medicine, engineering, chemistry, physics, and many other scientific fields are uniting under one roof at the University of Missouri's new International Institute of Nano and Molecular Medicine. The institute is headquartered in a new 30,000 square foot laboratory building. Inside, a team of 40 researchers and staff members conduct complementary projects using the most modern equipment and facilities. The new building houses several large synthetic and analytical chemistry laboratories, as well as mass spectrometry, nuclear magnetic resonance, and X-ray diffraction centers. The institute is led by Dr. Fred Hawthorne, a legend in the field of inorganic chemistry. After a long and distinguished career as a pioneer in boron chemistry, Dr. Hawthorne came to the University of Missouri in 2006. Today, Dr. Hawthorne has all the resources he needs to bring a life's work to full fruition.
Learning what the University of Missouri offers to scientists was one of my most important discoveries. This campus has everything I need to advance my research, including a collaborative attitude among faculty, an academic medical center, strong programs in biomedical and physical sciences, and most importantly, the world's best nuclear research reactor.
The University of Missouri's research reactor is the most powerful university reactor in the country. It offers more nuclear products and services than any other university research reactor, and it is the United States' sole supplier of the active ingredients in 2 FDA-approved radiopharmaceuticals. The reactor also provides new radioisotopes that researchers use for discovering innovative ways to diagnose and treat patients with cancer and other diseases. In August 2007, the university opened a 26,000 square foot addition to the reactor. The addition includes office and laboratory space, as well as a cyclotron that supports Dr. Hawthorne and other scientists. The reactor provides a thermal neutron beamline that will allow Dr. Hawthorne's institute to advance its research on boron neutron capture therapy, or BNCT. BNCT has potentially unequaled selectivity for the destruction of cancer cells. Rheumatoid arthritis radiotherapy is another possible use of BNCT.
With the addition of the neutron beamline, we now have the most unique and complete facility in the world for exploring and examining the chemistry required for boron neutron capture therapy.
First, boron agents, which are specific for tumor tissues, are injected into the patient. After a sufficient amount of time, the boron agents localize in tumor tissues and enter into cancer cells. Healthy cells do not contain boron, and after several hours, the blood is cleared of boron as well. The beam port door is opened, and the patient is loaded onto a hydraulic lift in the neutron beam facility. The hydraulic lift lowers and precisely aligns the patient with the neutron beam. The beam port door is closed to protect the technicians. The core of the nuclear reactor produces a wide spectrum of neutron energies and intense gamma radiation. The neutron beam port is actually like a window looking directly at the reactor core. The neutron beamline is constructed from exotic filters that act like nuclear sunglasses. These filters slow down the fast neutrons and remove nearly all of the gamma radiation. The beamline filters allow only clean, slow-moving neutrons to pass. These neutrons are now considered to be thermalized, as they now have only the kinetic energy of objects at room temperature. These thermal neutrons are now ready to be used in the BNCT reaction. Let's take a closer look at the reaction. BNCT combines 2 innocuous components, the isotope boron-10 and neutrons. The BNCT therapy operates through the highly selective delivery of boron to tumor tissues. Given a sufficient amount of time, which generally requires several hours, the blood and healthy tissues become free of boron. The tumor is then irradiated with neutrons. Boron-10 atoms, which are now inside tumor cells, capture the neutrons and fission to produce a helium nucleus, or alpha particle, and a lithium nucleus. These fast-moving particles possess 2.4 million electron volts of kinetic energy, and they deposit this energy over a very short distance, about 5 micrometers or a single cell diameter. In effect, The BNCT reaction produces a nuclear explosion fully contained in the space of a single cell. In a fraction of a second, the cancer cell is destroyed and all radiation completely disappears. The neutron irradiation requires approximately 20 minutes. After this is complete, the beam port door is opened and the lift raises the patient out of the facility.
This is my most exciting project. If it works as we believe it will, BNCT will be several times more effective than other similar agents for specific forms of cancer.
The International Institute of Nano and Molecular Medicine also conducts other fascinating research on new therapy and imaging agents, as well as highly selective drug delivery systems. One of the most intriguing projects involves the concept of molecular motors.
Molecular motors are single molecules that can be activated by light, electricity, or chemicals. When activated, they move in a predictable manner and deliver an infinitesimal but repeatable conversion to mechanical energy. Molecular motors could be coupled to other molecules, such as catalysts, for controlling chemical reactions. And if it works for chemical catalysts, maybe molecular motors could be positioned in front of selected cell surface receptors and act as doors for enzymes. By moving the motors, we could open and close the doors, which would give us control over biochemical reactions of targeted cells. The applications of molecular motors could even expand to improving energy sources and computers.
The University of Missouri couldn't be prouder of Dr. Hawthorne. In fact, his recruitment was a homecoming of sorts. Born in Fort Scott, Kansas, Dr. Hawthorne completed high school in Rolla, Missouri. At the age of 16, he enrolled in what is now the Missouri University of Science and Technology. In 1953, he received his PhD in organic chemistry from the University of California in Los Angeles under Nobel laureate Dr. Donald Cram. 3 years later, Dr. Hawthorne began to synthesize and study polyhedral borane clusters while working at the Rahm and Haas Company. Back then, no one knew much about boron chemistry. Dr. Hawthorne assumed it should be possible to do anything with boron that could already be done with its next-door neighbor on the periodic table, carbon. That assumption led to some of the most important accomplishments in chemistry. A member of the National Academy of Sciences, Dr. Hawthorne served more than 35 years on the faculty at the University of California in Los Angeles. In 1998, he was appointed University Professor of Chemistry, the most distinguished title bestowed on faculty by the Regents of the University of California. He served as editor-in-chief of the most cited journal in his field, Inorganic Chemistry, for more than 30 years, and he was a co-winner of the King Faisal International Prize for Science. In 2009, Dr. Hawthorne will receive the highest honor of the American Chemical Society, the Priestley Medal, for distinguished contributions to the field of chemistry.
The world has recognized that Dr. Hawthorne's research has seemingly limitless potential and applications. When you combine that with his energy and creativity, Dr. Hawthorne could very well lead the University of Missouri into a new era of scientific achievement. Now, as a physician and leader of the School of Medicine, I'm particularly excited about what Dr. Hawthorne's research could ultimately do for patients. For example, if we're able to use our medical center and other campus-wide resources to fully test and develop boron neutron capture therapy, we'll have made a tremendous contribution to medicine and to the lives of people throughout the world.
The future couldn't look brighter for the new International Institute of Nano and Molecular Medicine. A new life sciences incubator for technology transfer and commercial development is under construction behind the Institute and nearby Dalton Cardiovascular Research Center. At the same time, Dr. Hawthorne has nearly filled his new building with researchers and equipment.
We designed and constructed the Institute building during a period of 18 months. It was like a biomedical barn raising, with neighbors across campus coming together to offer all resources at their disposal. As we look forward to the potential addition of a new building and recruiting more scientists, I know I'll have the support I need because the people at the University of Missouri are born collaborators. Everyone is curious and supportive of each other's research, And that creates a very attractive environment for scientists like me to fulfill our dreams.